Along in your syllabus, then you'll see that I was supposed to do 2.3 and 2.4 together in the same day, which is doable, and that's why I have it in there that way. But we were actually a day ahead, and so I felt like I could slow down. So I did 2.3, and then today I'm going to do 2.4, which puts us right back exactly where the syllabus said we would be. Right? So that means, unless something strange happens, our first exam will be when the syllabus says it will be, and that's coming right up. That's September the 22nd, which is a Wednesday. So you need to already be looking ahead a little bit. So today, section 2.4 is about measures of spread of a distribution. So if you think about it, when you have a distribution, and you want to describe that distribution to somebody, there's three characteristics of the distribution that once you tell them that, they ought to be able to get a pretty good sketch of what that distribution looks like. Right? So the first characteristic would be its general shape. If you tell me, oh, it's normal and bell-shaped and symmetric, then I have an idea what that looks like. Or it's bimodal, or it's skewed to the left, or it's skewed to the right. Okay? What do you think the second thing that you would need to tell them is? Like if I want to draw the distribution, what's the next thing I need to know to be able to draw it? Okay, we talked about shape, so I already got the skew or whatever. Okay, how high up? I'm going to come back to that one. Think about a number line. All right, I draw a number line from negative infinity to infinity. Where do I put that distribution? Yeah, how do I know where to position it? You got to give me some kind of a measure. Okay, a range, or what I'm looking for, nobody's going to say it, is a measure of the center of the distribution, which we did in section 2.3. You tell me, oh, pulses are bell-shaped and symmetric, and they're centered at 72 beats a minute, then I can draw a symmetric bell-shaped distribution. Isn't that pretty? A symmetric bell-shaped distribution, and I know that the center of it is at about 72. Right? Now, what you said, who said how high it is? Somebody said that. Right? And I heard somebody else say the range. Right? The range. Meaning, what's the smallest pulse, what's the largest pulse? Both of those are measures of spread. And that's today's section. Right? Because I could draw a bell-shaped symmetric distribution centered at 72 that looks like this one, or I could draw one that looks like that. Very different distributions. This distribution is a lot more spread out than this distribution. Okay? So as you can tell, the range here would be much smaller than it would be for that one. Okay. So that's the first measure of spread that we'll talk about, is the range. Now when you hear the word range, what do you think of? Actually, let me pop up here the distribution for the pulses. Look at that picture and tell me what's the range of pulses. 42 to 104. That's right, but that's wrong. Technically, in the book and in statistics, range is the max minus the min. But almost everybody, including me, if somebody says, what's the range of pulses, I'll do exactly what Eddie said. I'll give you the smallest value and I'll give you the biggest value. I'll say they ranged from 42 to 104. But technically, it's the difference between the two. It's a single number, which would be 62. So that's 104 minus 42, which is 62. That's the range. But you know, if my mom's asking me about pulses, and she says, what's the range? And I say, the range? It's 62. That's not what I meant. You know? What do you mean, 62? What's the smallest? What's the largest? That's what people know. So it's okay to answer the question that way. Just know that when you do the online homework or a test for me, and I have a blank that says range, what is the range? I want 62. Okay? And in fact, that's the way the statistical software is set up. If you look at this output, which I've shown several times, there it says range 62. So it's just a measure of spread. There's 62 units between the smallest and the largest observation. Now remember when we were talking about the difference between mean and median? We said one of those is resistant to outliers and the other one is not. Which was which? Okay, the median is resistant, the mean is not. What about the range as a measure of spread? Is it resistant to outliers? No, not at all. That's the only thing it uses in this calculation are the two most outlying observations. So it's not a real good measure of spread because one big outlier can just completely distort. So we need better measures of spread. And there are several other measures that we're going to talk about in this class, but the main one in this section is the standard deviation. And that's the one up there at the top. STD, short for standard deviation. Another one, which is in the next section, in section 2.5, is the interquartile range. And notice the interquartile range and the standard deviation are fairly close together. And the interquartile range is always slightly bigger than the standard deviation, but in the same magnitude, whereas the range is a lot bigger. Okay, so standard deviation. Let me give you a pictorial view of what standard deviation is, and then we'll give you a formula for it. Now, I've raised the screen up so that I can write on this without getting in trouble. Right? We've described the distribution as being roughly bell-shaped and symmetric, and it's centered at about 72. So it's centered right about there. One standard deviation turns out to be, whenever you have a bell-shaped symmetric distribution, one standard deviation is about halfway down the hill. So if I start here at the top of the blue curve, and I come down about halfway, it looks like about, right in there. So I go down, and it's at about 82. So I'm going to draw a dotted line up to the curve at that point. I didn't go real vertical, but yeah.
Is it halfway just left and right, or halfway along the diagonal curve?
It's think of like here's the hill, there's the hill, come about halfway down, right?
Okay. But like if it's really, really steep and you only come halfway down, you're not going to go out as far.
Right, exactly. So if I have a really, really steep curve like this, then halfway down the hill is about right there. And that's going to bring me down vertically to here. So there's the mean. That distance is one standard deviation. So here, this distance is one standard deviation. So what is that distance? It's about 10. Remember what it was on the previous slide? Anybody look at it?
13?
No, that was the interquartile range. Whoops. Standard deviation, about 10. And it always works that way. It's cool. If the distribution is bell-shaped and symmetric, then you can look at a picture and estimate the standard deviation without having to have any numbers. You can just say, well, if I go about halfway down the hill, that takes me this many units away from the mean, and I need my other picture back. That takes me about 10 units away from the mean, and therefore my standard deviation is about 10. If I come down the other way, then I go about halfway down the hill, that's about right there, and I come down, and that's at about 62. 10 units the other side. Okay? So I'll draw a dotted line up there. Now notice on that graph that most of the population, or most of the sample, falls inside those two dotted lines. So what we would say is they fall within one standard deviation of the mean. How much of the distribution does it look like is in there? Just a rough guess. Does it look like half of it's in there? Does it look more than half? More than half? Does it look 3/4? Kind of getting in the ballpark. Well, to me, it looks like it's about 68%. Okay? If you have a very symmetric, very normal distribution, then approximately 68% of the population will fall within one standard deviation of the mean. Okay? And if it's not perfectly normal, then it isn't going to match that exactly. But the closer it is to bell-shaped and symmetric, the closer that percent will come to 68%. So 68% is about 2/3. So you could say about 2/3 of the population falls within one standard deviation of the mean. Now if I go out 2 standard deviations from the mean, that means go from the mean 10 units to 82 and another 10 to 92, and this direction another 10 to 52, and I draw dotted lines there. Any guesses as to what percent of the population would fall in there? 95. That's a good guess. Where'd you get that number? Out of the book. You mean you read the book?
And the homework.
All right. 95% of the population should fall within 2 standard deviations. So it's 68 within 1, 95 within 2. Let's go one more. If I go out to 102 and down to 42, it's not quite 100%. It's what my grandmother would say is pert near everybody. We're in Kansas. The author of the book says all or nearly all. Well, he's from Boston. That's how they talk in Boston. In Kansas, we say pert near everybody. So we got 99.7% is within 3 standard deviations of the mean. This is called the empirical rule. So you have 68%, 95%, and 99.7%. 68% is the mean. Remember the Greek letter mu? That's the parameter for mean. Plus and minus 1 standard deviation. Now, I don't know if I've shown you that before. Okay, so let me write that over here. The Greek letter sigma, this is lowercase sigma. Remember, this is uppercase sigma, and that means what? Summation. So lowercase sigma is the population standard deviation. Remember, we have mu for population mean. What was the sample mean notation? X with a bar over it. We call it X bar. So X bar is sample mean, mu is population mean. Sigma is the population standard deviation, And S, lowercase s, and usually I'll put a little subscript on there to say what variable I'm talking about, is the sample standard deviation. Okay. And same thing with the sigma. A lot of times I'll put a little subscript of an x. And all that indicates is which variable I'm talking about. So I might have an x and a y and a z, and I've got sigma sub x, sigma sub y, sigma sub z, meaning standard deviation of the different variables. Okay? So this empirical rule works whether it's mu and sigma or x bar and s. It doesn't matter. It still holds. So I'm writing it with the population parameters right now. Mu plus or minus 2 sigma gives me 95%. And mu plus or minus 3 sigma gives me 99.7%.
That only works with it if it's normal and bell-shaped.
Exactly. This will not work well with the age distribution. Okay. It does not work well with the age distribution. And in fact, I forgot to do it for today, but usually I go back to our data, 385 observations, and actually count the percent that was within 1, 2, and 3 standard deviations. And for pulse and for height, it works really well. It's always real close to those numbers. You know, it might get 70% instead of 68%. But for the age distribution, it's always way too big for the first one, and then gets too small for these. This one might actually only be about 80% instead of 99.7% for the age distribution. So it works well with bell-shaped symmetric distributions. Okay? So that's the empirical rule based on standard deviation. So now let's kind of dissect this idea of standard deviation and build a formula for it. I'll turn off the projector so that it's not clouding up my screen here. What does that term make you think of when you say standard deviation? What does the word deviation mean? How far away from something? Good. Now, in this definition, we have to say, okay, how far away from what? Okay, mode or mean or median. All of those are measures of spread, right? Well, the standard deviation is defined as distance away from the mean. There are other ones that are distances away from the other measures of center, but they don't hardly ever get used, so we don't even teach it in here. So deviation is distance from the mean. So if the mean heart rate, I'm going to use it as a sample mean, if the mean heart rate is 72, and my heart rate, call it X, is 60, now let's say 80, what's my deviation? It's not that tough of math. 8. And how'd you get that? Well, X minus X bar is a deviation. Right? So 80 minus 72 minus 8. Okay? Now Garrett's heart rate back here is about 60, right? Yeah. So for his X value of 60, what's his deviation? Almost. It's not 12, it's negative 12. Right? So we have 60 minus 72, which is negative 12. And the negative is important. The negative tells us, oh, that number's below the mean. So you can look at my heart rate at 80 and say, 8, well, he's 8 units above the mean. And Garrett is 12 units below the mean. So what we want from standard deviation is the standard amount of deviation across the whole data set. Well, they're careful not to call it the average deviation. And I'll show you why in just a second. But think of it that way. Standard or typical amount of deviation. Okay? And the reason that it's not the average deviation, if I want to do an average, I add them up and I divide by the sample size, right? So if I add up the deviations, guess what they add to? Some are positive, some are negative. 0. By definition, these will always add to 0. Because that's by definition of the mean. The mean is the center, it's the balance point, so there has to be an equal magnitude of positive deviations and negative deviations. If there wasn't, the mean wouldn't be right there, right? The mean automatically has to go to that point that balances out the deviations. So this doesn't work. I can't average the deviations because it would always be 0. So the negatives are a problem. Now, mathematics, when negatives are a problem, how do you get rid of them? What can you do to a number to get rid of the negative? Okay, that works if it's a negative. What if it's a positive and you multiply by negative? Now you made it negative. So multiply by -1 is a good thought, but any other ideas? Square it. If you square it, things that are negative become positive. Things that are positive stay positive, right? So you can square the deviations. There's another thing that usually somebody says. Absolute value. You heard of that? Take the absolute value. There is a measure of spread that's based on the absolute deviations, and it's called, you don't have to write this down because it's not even in the book, but it's called the MAD. I like it just because of its name. The MAD. Anybody guess what MAD stands for? It's an acronym.
Measure of absolute distance.
Almost. The first word is mean. Mean absolute deviation. So you just take the absolute value of everybody's deviation, average them, and you got the mean absolute deviation. It is a measure of spread. But it doesn't get used very often. So what we do is we use the square deviation. So taking this, instead of average or summing up the deviations, we square the deviations, and then we sum them up. And then to average them, you divide by how many you added up, right? Well, almost. Instead of dividing by n, we actually divide by n minus 1. Now, why in the heck do you suppose they divide by n minus 1? Just to make it harder to remember. Well, that's not quite the reason. There's really, it's kind of a complicated thing of why it's an n minus 1 and not an n. But I'll give you 2 quick arguments for that. The first one is just kind of a common sense thing. This is the sample standard deviation, right? Oh, actually, before I get into why it's n minus 1, let me finish this. We'll let S sub x be standard deviation, but this is in units of squared whatever it is. If we're doing heart rate, then it's squared beats per minute. And I don't like squared beats per minute because I have no idea how to interpret that. So if I take the square root of this, after I finish the calculation, I take the square root, then I'm back in the units I started with. So the standard deviation is back, or has the square root. So you're back into your units that you started with. Okay? Now, back to the n minus 1. If you're going to estimate the spread in the population based on the spread you saw in your sample, you know that when you take a sample, there's almost no chance that you got the biggest value in the population or the smallest value in the population. So you're going to underestimate the total variability based on a sample. So if you underestimate, that means your number's too small. So to adjust for that, you make the bottom of the fraction slightly smaller, you make the value of the fraction slightly bigger, right? And the amount that it underestimates depends on the sample size. If you take a sample size 5, you're probably going to way underestimate, right? So subtracting 1, you go from a 5 to a 4, that's a bigger magnitude change than going from 500 to 499. That doesn't have very much effect at all. But the real statistical reason why it's n minus 1 has to do with degrees of freedom. And this is something the author doesn't introduce until chapter 6 or 7, somewhere in there. But I like to do it here because it pops up. Degrees of freedom are n minus 1. So what you're really dividing by are the degrees of freedom. Now what the heck does degrees of freedom mean? Well, here's a quick little illustration to give you an idea what degrees of freedom means. Let's make up a really small data set. Okay? 4 observations in this data set. And the mean of the data set is 10. So I'll go around the room and ask you to give me a number. Pick anything you want. Right? What was your name again?
Casey.
Casey. That's 12. Okay? Alright. Caitlin? Caitlin, yeah. What? 16. Okay? And let's see. Delaney?
8.
8. Okay? And how about Aaron?
3.
3. Is 3 okay? I said I wanted the mean to be 10. Does the mean of this give us 10? What do they have to add up to give me a mean of 10? 40. So this is, how much is that?
36, 39. One short.
Did we just, we're that close? Yeah, let's see, 28, 11, yep, 39. So 3 doesn't work. That was close. It has to be a 4, right? Now what just happened? I had 4 blanks, and I called on 4 people. The first 3 of those people were free, degrees of freedom, were free to choose whatever number they wanted. But by the time we got to Aaron, we had used up all the degrees of freedom. She now had to figure out, which I set her up to fail. You know, I didn't say, by the way, make sure the mean turns out to be 10. Right? She had to figure out what that last one has to be. Once you fix the mean, then there's only n minus 1 values that are free. The last one is then fixed. So there's n minus 1 degrees of freedom in this calculation because x bar has to already be known. X bar is in the formula. So you aren't adding up n independent observations. Once you add up the first n minus 1 of them, I can tell you what the last one is just by computation. Right? So you divide by the number of degrees of freedom, not by n. Okay? So this is the formula for standard deviation. Okay? Now, I don't think that anywhere on the online homework or in an exam that I'm going to give, I don't think we ever make you compute standard deviation by hand. But just for fun, and trust me, it is fun. Did you in your other stats class? Let's take KMW. You can't see it. KMW, that's Kristen Wurst, right? Caitlin Wurst. There's her 5 observations. And let's look at the pulse. Okay? Now, on your calculator, we showed you how to compute the mean and the median and all that stuff. You remember how to do that? Anybody? First, you do what?
That,
First, you push the Stat button, then Edit, and that takes you into the List editor, and then you enter those 5 pulses. Okay? Now, I have the software that'll let me emulate, but I don't want to pull it out because then I'd cover this up. But, and then once you get the data entered, okay, so enter into L1 those values, 70, 60, 74, 64, and 100. Then what do you do next? Once you get the data entered, you push Stat, then Calc,
one,
and then 1 var Stats, and press Enter. And then you go second function L1 and press Enter. Okay. Now, read off to me the top line, which is X bar. What is that? 73.6. Yep. Okay. Notice that she actually did very well in terms of estimating the overall mean. The overall mean was 71.8 or something, and she was only less than 2 units away from that. Then you go down, there's a couple things we don't care about, sum of x squared. The next one down is SX. That's standard deviation. What is that? 17 or 15.70. It'd be a 1 if I go to 2 decimal places. Okay, we'll stop there. Okay, so 15.71. Now, if I was going to do this by hand, let me dim the projector. The best way to do it is to make a little table and at the bottom compute X bar, and then X minus X bar, make a column for that. Now, I'm not going to go all the way through this, but I'm just going to show how you would set it up, and then you can finish it yourself because it's fun. 70 minus 73.6. What is that value? Negative 3.6, right? That one I can probably do in my head. Okay? And the next one is 60 minus 73.6, which is negative 13.6. And then 74, and that's 1.4. No, it's just 0.4, right? 0.4, and I'll say dot, dot, dot. So the first thing you do is you get the deviations from the mean. Then what's the next thing you do? You got the deviations of the mean. Next thing is square them. So then you square each of those numbers. So negative 3.6 squared is what? How much?
12.96.
12.96. Okay? We'll do one more. What's negative 13.6 squared? 184.96. Okay? Then we'll say dot, dot, dot. Actually, this one I can do in my head. That's 0.16. Right? So some of them have really big squared deviations, some have really small squared deviations. Then what's the next thing that this formula says to do? Sum them up. Right? So sum up that column. So So down at the bottom of this, you'll have the sum, and that's the sum of x minus x bar squared, and you get whatever that sum is. Okay? Some number. And then you divide it by, what do you divide by?
Degrees of freedom.
Degrees of freedom. And that is, in this case, 4. We have 5 observations. 5 minus 1 is 4. So you're going to take whatever that sum is, divide it by 4. Then whatever number you get there, take square root, and you got it. And I just went ahead and did it in my head, and I got 15.71.
Such a genius.
Yeah, I'm a genius. Okay? So did everybody understand how to get standard deviation out of your calculator? Now what's the line that's right under SX? I saw, it's Teresa, right? I saw Teresa do this.
Something like that.
Like, I don't know what that thing's called, but it was that squiggly thing you drew a minute ago. It's sigma, lowercase
I
sigma.
wasn't sure if I was right, so that's why I said.
Yeah, that's what it is.
I can say
And
no.
what was that number, by the way? Does anybody still have it on the calculator? 14.05, something. Okay. What's the difference here? What is this one? And of course, I walked over and I erased what I wanted now to point at, so it's not there. But that's the population. Well, that's what that means is if those 5 people in that data set were the entire population, then this is what the standard deviation is. The only thing different between these two numbers is this one, sigma x, divides by 5 instead of 4. Right? So we won't ever use this in this class except for one time, and that's when we're doing probability distributions. So when we do probabilities, we'll be interested in the population standard deviation, but until then, and then after that, we'll always deal with SX and not sigma x. All right? A very common mistake on the first exam is I'll say, what's the standard deviation of these 5 numbers? And they'll give me the number that's 14.05 instead of the SX number. So just be careful on that. Okay. Let me come back to the slideshow. And let's go down to there's women's heights. Let me make it full screen. Looking at nothing except that picture, estimate for me the standard deviation. I like to put things like this on test questions. Give you a picture and ask you several questions about the picture, one of which is, what's a rough estimate of the standard deviation? Who over here said about 3? Somebody did. You did? A lot of you raised your hands. Yeah.
It's just from the center to the one side, not from both.
It should be the same in both directions, so you just have to do one of them.
Just one.
That's right. So looking, it's easiest if you kind of cheat and use the blue curve, right? But still, the center of the distribution, it looks like it's about the same place. But you start here, there's your center, and that's at about 65, a little bit less than 65 maybe. So we'll call it 64.5. And I come about halfway down the hill, so about right in there, right? And I drop straight down, and I'm about 68, not quite 68. So here I was not quite 65 to not quite 68, about 3, right? And the same going the other way. Now we do have two outliers in women's height. And outliers, the standard deviation is not real resistant to outliers. It's much better than the range, but it's still, outliers can affect it. So these will tend to inflate the standard deviation a little bit. If I drop these two out and recompute, I'll get a smaller number. Okay. But let me page down so we can see what the standard deviation actually is and compare to our about 3. So there is standard deviation 3.16, about 3. See, it's pretty easy actually. If you have a nice bell-shaped and symmetric distribution, it's fairly easy to estimate the standard deviation from that. What if I had that distribution? Estimate the standard deviation. All bets are off, right? You can't say, well, halfway down the hill, you'd have a really small estimate of standard deviation and you're ignoring this huge long tail. Now this one you can actually cheat a little bit because of the blue curve. I told the program to fit a normal distribution to this data. Obviously it doesn't fit very well, but the standard deviation, it's going to use the sample standard deviation to set the spread of this thing. So if I start at the blue curve and I go halfway down the hill, it looks like I'm about right there, which is out to what, 43? And the mean is wherever it's peaked at about 29. So 29 to 43 is 14. Okay?
Have you ever combined all the data from every year on that one that you just showed?
Yeah. I got all semesters put together. Now we said about 14, and there it is, 13.4. But again, if that blue curve wasn't on there, you would have no idea. There'd be no way to estimate it. It doesn't work unless it's bell-shaped and symmetric. Right? Eddie was asking about pulling the data together. What are you interested in knowing?
It'd be cool to see through the 3 humps because
Yeah.
of the
I have that data pooled together. I just haven't put it into a slide. So send me an email, remind me, and when we come back next time, I can show that slide. That would be interesting to look at. Okay, I got just enough time left to do 1 or 2 homework problems at the end of the section. Whenever I have time, I like to do that because it's the same problems that your online homework is based off of. So let me get this stuff out of the way. I'm going to work number 55 at the end of section 2.4, which is on page 64 if you have your book with you. And I'll read it and then I'll write stuff on the board. It says, the college athletes data file on the text CD has data for 64 female college athletes. The data on weight in pounds are roughly bell-shaped with a mean of 133 and a standard deviation of 17. So they have a mean of 133, and it's an X bar because it's a sample of 64 female college athletes, not the whole population. And it's S of 17, not sigma. And he doesn't do it in the book, but I'm going to put a sub X on there because that's what you're used to seeing out of your calculator. Part A says, give an interval within which about 95% of weights fall. Everybody's going 2. 2 what?
deviation.
2 standard deviations from the mean. So what I want to do is I want to go 95% will be X bar plus and minus 2 standard deviations. So X bar is 133, SX is 17, 2 times 17 is 34, so 133 plus or minus 34, and I might even be able to do that one in my head. The interval is then 99 to 167. Everybody follow that? So what is that saying? Interpret that.
That 95% of the sample fall between 99 and what's it say?
Okay, exactly. She said 95% of the sample. And I'm going to say it a little bit different. I'm going to say 95% of college female athletes have weights between 99 and 167. Now I said it more like it's a population statement, which isn't correct. And what Carolee, right? What Carolee said was of the sample, and that's more precise because this was just sample data. But then we might want to make inference to the whole population, which we would then say, therefore we believe that approximately 95% of the population would be in that interval. Okay? If they ask you for an interval with 68% of female college athletes, then you would go 1 standard deviation. If they ask you for all or nearly all, or if they ask for 99.7, then you would do 3 standard deviations. What if they ask you for something like 80%? Give me an interval that has 80% of the women between. Well, then you're just hosed. Right? When we get to chapter 5, then you can work that problem, where we do probabilities based on a normal distribution. But until then, the only thing we have are nice integer multiples of number of standard deviations. Okay? Now this concept of number of standard deviations is something called a z-score, which is in section 2.5, which we'll do next time. Part B on this problem says, identify the weight of an athlete who is 3 standard deviations above the mean. Identify the weight that is 3 standard deviations above the mean. Well, the mean is 133. So what do I do? Actually, they only said above, so I don't have to do the minus. So just plus 3 times 17. What is it? 3 times 17 is 51. Okay, so then add that to 133 and you get 184. Okay, so 184. So a female athlete that weighs 184 pounds would be 3 standard deviations above the mean. Now, the next question says, would this be a rather unusual observation? What's your answer to that question?
Yes.
Would it be unusual to find a female college athlete that weighs 184 pounds? Yes. It would be incredibly unusual based on this data because that's 3 standard deviations from the mean. Remember, 99.7% of all female college athletes should weigh less than that. Right? So only 0.3% would weigh 184 or above. It's actually half of that, but we'll get to there later. So the answer is yes, that's highly unusual. Being 3 standard deviations away from the mean in any distribution is exceedingly rare. Okay? All right, have a great Labor Day weekend, and we'll see you back here on Wednesday to do section 2.5.